Hey guys, this is your first lesson on thermodynamics. I know you did the chemistry energy thoughts. Interested in reading your response. We're going to talk about this is our first kind of real learning target. Apply the first law of thermodynamics in the equation, and you'll get to know these equations here. Alrighty. So what is thermodynamics? It's the study of heat and other forms of energy. And by energy, you can have mechanical energy, electrical energy, or chemical energy. And chemical energy is kind of really what we talk about, the study of energy and changes that occur during chemical reactions. So breaking bonds, doing stuff like that is forms chemical energy. What is energy? The definition of energy is the capacity to do work. Okay, so like to move matter. Potential energy is the position that it's stored, and kinetic is moving. So like the classic example is if a car is standing still, it's got it on the top of your driveway. It's got a lot of potential energy. Actually moving it down the driveway is what we call kinetic energy. That's a lot of physics in there. As far as what we do, we talk about the system, and it's whatever the part of the universe is being studied. Surroundings is the rest, and your system is just very broad. It's very loose term. A system could be this room I'm sitting in, and then the surroundings would be my house. It can be anything, but it's got to be clearly defined. There's three different types of systems. Okay, open, closed, and isolated. So open obviously is what it is. Energy can release, and that's why your coffee gets cold. A closed, meaning that like energy can cool, it can no matters exchanged, but it definitely can go back and forth. And then an isolated system is definitely what we call like a vacuum thing, and that's what a lot of like Yeti mugs and stuff try to do, is try to lose the exchange of energy to keep it hot or cold or whatever have you. All right, so the definition for the internal energy is this, U. All right, internal energy is the total energy contained in the system. Part of U is kinetic energy, transmotional energy, rotational energy, vibrational, and thermal. Part of U is potential, all right, and so it's just a very broad term, right? So like you can have molecules moving is energy, bonds stretching, that's and moving, that's the type of energy. Breaking bonds and moving things, that's chemical energy. Heat is Q, okay? So the energy transfer between a system and its surroundings caused by the temperature difference, all right? So heat is Q. So internal energy is U, Q is heat. And when we say heat lost or heat gained, we actually mean energy is lost and energy is gained. So we kind of use that a little bit loosely. You really don't have heat. Energy creates heat. Okay, so that's just kind of the definition of that. Equal thermal equilibrium, when a system reaches the same temperature. This is a huge point. Heat always flows from high to low. All right, so like if you think about your house, it's hot. Okay, when you open a window in the winter, the heat is going to flow that way. It's not that cold air rushes in, it's that heat is going out. So everything goes from high to low. Same thing with pressure. Everything flows from a high pressure to a low pressure. So when you talk about meteorology, or not meteorology, yeah, meteorology, you're talking about like, hey, here's a storm system, which is a low pressure system, and you have a high pressure system like it is today. It's super nice out. The wind goes from the high pressure system to the low pressure system. So everything flows from high to low. If you're in an airplane and there's a leak, well, you have a high pressure because you need pressure to breathe in there, and low pressure outside the plane, everything goes out if there's a leak in the plane, and that's what kind of causes all the damage. So everything goes from high to low, and so does heat. Work. What is work? Okay, work is energy transfer between a system and its surroundings due to a force applied over a distance. So work is pressure volume. So this work is really only worrisome or we care about in a closed system. So like your car engine is a closed system and it does work, and it's the pistons. So let's say you got your car engine. I'm a great artist. okay, and you have it's a closed system, and you have your pistons, and then you have a chemical reaction, and you have the pistons firing, and then going back and down. That's a closed system, and that's pressure, and what causes it to change is the pressure, and the difference in volume. You can calculate how much work a car engine would do. Here's another example when a gas expands. So here's the initial state. Boom, there's initial volume there. It expands. How much work is being done is what you can calculate on that. So work is negative pressure, okay, and then delta V. But we're not going to get too far into this because here's an example. Calculate the work done with the volume expands from 12 liters to 14.5 with an external pressure of 5 atmospheres. So basically what you're saying is, hey, what's the work being done if I had negative 5 atmospheres times delta V, which is the difference here. All right, so that's how you can calculate work. That would be like work of a closed system. Another thing we're dealing with thermodynamics is state functions and path functions. Okay, a state function like doesn't really care. So if I'm here, okay, and this is Blaine High School. If this is Blaine High School, the state function, I get to work, okay, it doesn't really matter how I got there. If I'm driving from Ham Lake, all that matters is that I got there. So that's the definition of a state function. A path function cares about which way we go, all right? And reality is state function is really what we care about because in chemistry, we really don't see all the middle. We just see the beginning and the end. Here's an example of a state function. This car, poor guy, he's got to push his car all the way up. So that's a path function all the way up. This is a state function. Who cares? You just got there. It doesn't matter. You get to the same thing. So the first law of thermodynamics, why do we care about thermodynamics, is this. We must count for all the energy transfer to know what the internal energy of a system. So here's our delta U, and the internal energy of a system is heat plus work, all right? So it states that the total energy of an isolated system, keyword isolated, is constant. So you can't create or destroy energy. Same thing with like the law of conservation of mass. You can't just create or destroy or particles, right? So if you have a chemical reaction, the chemical reaction in that vessel is going to be constant. The energy is going to be constant. What you break and what you form is going to be the same no matter what, all right? Just some signs that you really need to know. If heat is absorbed, it's positive. If work is done on the system, it's positive. If energy is leaving a system, its Q is negative. So basically saying that if its heat is given off, and this is heat absorbed. All right. If work is done on the system, meaning that it's being worked on, it's positive. If work is being an output, okay, if doing work, it's negative. All right, just to keep that in your back pocket. A gas does, so let's just figure out, we're going to figure out delta U, the internal energy. A gas does 135 joules of work while expanding. It absorbs 156 joules of heat. Okay, so I have Q plus W. All right, so delta U is equal to what we would say, so gas does work. Let's go back and check the signs. Does work. Work is done or work is being done by the system, so it's negative. So negative, so negative 135, and it is absorbs, so meaning it's getting 135 joules, so plus. That was, whoa, I wrote that wrong, sorry, 156. Okay, so I can calculate the internal energy. The hard part is figuring out what the signage is. Let me do that again. A gas does work, so it's outputting, okay, and it absorbs, it's positive. That's how you would figure that out. And then you could calculate the delta U of the system there, which basically means that I'll have 21 joules then of energy, okay, between losing heat and work being done on the system. That's that. So just so just for our purposes, okay, internal energy is U, work is W, heat is Q. Okay, just a summary. The equation for work is equal to the negative P delta V. Okay, the equation for internal energy is delta U, or excuse me, U is equal to Q plus W. So ultimately what you can say is you can say U is equal to Q plus negative P delta V. Remember, this is for a closed system, okay? So the system has to be closed to be able to figure this part out right here. If it's not closed, we don't care. If work is being done on the system, it's positive. If the system is outputting work, it's negative. Heat is being absorbed by the system, it's positive. If heat is being given off by the system, it's negative. So here's your problems, okay? Don't sweat tons on this, because really what we care about is this is just like the basis of thermodynamics. All right, can a system do work and absorb uh, heat at the same time? The answer is yes. Okay, the answer is yes. They just would. So if a system can do work, okay, so do work would be negative W, and absorb heat at the same time, it'd be plus Q. Okay, they just would have to be the same. All right. And for this here, these two problems, just get used to plugging in, okay, what we know, and then just plug in your variables and solve them, check your answers. So like I said, guys, don't sweat over this. Um, it's really probably on a scale of 1 to 10, it's a 1. But it's just at least getting you used to what we care about. Alrighty. Then there's just a couple other terms that we'll kind of get into in the next video here.